Well, the only potential, I guess you can turn the thing on.
It is on.
It's on. The only problem here comes from the thing multiplying x. And the real part, being negative, means everything converges. Oh,
And this is square.
oh,
No, there's no square.
well, wait a
W
minute.
squared.
Now, the real part, you see, you have to be careful here.
Not in the
If you have a real part
In the book it says W.
of w, and you're integrating x from minus infinity to plus infinity, then the real part of w doesn't help you.
No, I think I missed a
No.
square in the thing. It's x plus
It's like
z
W is
squared.
like the square root.
X is squared?
X plus z whole squared. Yep, that's next one.
Okay, all right. So z is basically irrelevant, and yeah. Well, the imaginary part just gives you a sign, an oscillating thing that basically cancels itself. It makes it more convergent.
Okay. Okay.
In fact, this is the origin of a problem that has been dawning on people for the last 20 years, more than that, the last 40 years. And it's called the sign problem. Because you can essentially use the Monte Carlo method to basically estimate anything. But if the action or the energy is complex rather than real and positive, then you can rework the thing so that you write the thing you're trying to find, the mean value of some observable, is a ratio of two ratios, actually. And the trouble is the ratio on the bottom, because of the oscillations, gets very, very, very small, and so your errors just go crazy. But in general, when things oscillate, in fact, the reason why we're not just all waves, and in other words, why our wave nature is suppressed, is because of these oscillations that cancel. Actually, we don't have a wave nature. We're really particles. We obey a wave equation. It's what we do. And the wave equation has these oscillations in it so that quantum mechanical aspects, the macroscopic phenomena, by and large, cancel themselves out. Okay, sorry for that very long-winded, tangential explanation. But come see me. By the way, I keep forgetting to say this. My office, of course, is 176, and I'm there most afternoons and even most evenings. Well, not at dinner time, but afternoon. And so if you have questions, just wander by. You'll probably find you stuck on something and glad to see you. Okay, so we were talking about various differential equations, and by the way, you see these wounds. I was running to a doctor's appointment, and the sidewalk in front of Carrie Tingley Hospital is uneven, and I tripped, because the sidewalks throughout most cities, except for New York, are uneven. I grew up in New York. So I'm used to running on flat surfaces. Okay. By the way, let me just say something about hospitals. They don't all charge the same rates. And by and large, you're better off going to university hospitals rather than private hospitals. Private hospitals charge more, and they use the money to pay the president of the hospital $1 gazillion a year. And because the doctors make so much money, they don't know what to do with it. Whereas as the University of New Mexico Hospital is. They also pay their doctors quite a bit, but they keep things reasonable and they try to charge reasonable rates. Also, the medicine is normally better at academic hospitals than at profit-making hospitals. Because of the profit-making hospitals, the doctors are always on vacation, trying to spend the money that they charge for the patients. The reason I bring this up is that I made the mistake of having a stress test at Press. The charge was $200 more than the stress test at the University Hospital.
Stress test is the
So we need a single payer health care. Obamacare is a step in the right direction, but we need a forced march. Okay, so let's see. We were basically saying that, let me just remind you that functions, if you can find function numbers K1, K2, and so forth, such that this linear combination vanishes, then with some of the k's non-zero, so some ki not equal to 0, then the k's, but not the k's, then the y's are linearly dependent. So, on the other hand, and if they're linearly dependent, that means basically you don't need all of them. And so you just use the linearly independent ones. And so suppose we have some nth order ordinary differential equation, which, and in fact I'm speaking generally, and so what we're talking about here is some hm of x dm y dx to the m equals, if we're saying it equals 0, then this is a homogeneous nth order. So homo nth order ordinary because we only have x derivatives, and homogeneous because we have a 0 here. And most importantly, linear. And linear because the unknown function occurs to the first power, not to the second or third, no funny logarithms or anything. And then also not to the 0th power, because if with the 0th power you have an inhomogeneous term, a source term. By the way, somebody asked a question and I forgot to give it to Andy. And also there's a person who runs the camera. Okay, so since these are all solutions, so we can say, well, K is maybe a bad choice here. J, say, of x equals 0, we can add them together and form a solution, and we can then say that any linear combination like this, AJ, I don't know quite why I said, I switched to F from Y. All right, let me stay with Y. We can say that any linear combination of these y's is clearly a solution, and if these y's are not only linearly independent, but if they are complete in the space of solutions, that is to say, if we can express any solution of this differential equation in terms of these, and by and large, it's basically j equals 1 to n, there typically are n solutions of n linearly independent solutions of an nth order homogeneous linear ordinary differential equation. So that's the situation for the most, this is then the general solution. And now one can consider the same equation, but where it's of the form hm dm y dxm equals now s of x. And so, of course, we can say, and I'm going to rewrite that, I'm going to write the homogeneous equation as LF equals 0, and the inhomogeneous one as LF equals S. So, if we have two solutions, let's suppose we have two solutions of the inhomogeneous equation. In fact, maybe what I should do is stay with y's for this. So I'll use y for the, at least for this part of the lecture, I'll use y for the solution of the homogeneous equation, and f for a solution of the inhomogeneous equation. Since the differential operator is linear, this is LF1 minus LF2. And that's equal to s minus s, which equals 0. So that means that the difference of any two solutions of the inhomogeneous equation is a solution of the homogeneous equation. So we can write f1 of x minus f2 of x must equal some j equals 1 to n aj, and I'm going to use a y here, yj of x. And what that means is that any solution of the inhomogeneous differential equation is equal to any other solution of the inhomogeneous equation plus the general solution of the homogeneous equation. So this is the general solution homogeneous equation. And this one is any solution at all of the inhomogeneous equation. So the most general, and this is any solution of the inhomogeneous equation. So what this means is the general solution of the inhomogeneous equation is any old solution of the inhomogeneous equation plus the general solution of the homogeneous equation. So in other words, sometimes when you have an inhomogeneous differential equation, you can find a really trivial solution of the inhomogeneous equation. That works. You use that as F2, and then you use whatever you want here to be, well, you put here the general solution of the homogeneous equation. All right. Now, of course, if you have partial differential equations, well, let us, all right, so now I'm going to abandon this y business and just talk here of some sort of coefficients m1, mk of x, partial m1 plus mk partial x1 to the m1 partial xk to the mk of f of x. And of course I'm using x for x1 through xk. And if we're talking about a homogeneous equation, then it's equal to 0. So this is a general linear partial differential equation. And of course, a partial differential equation is a whole equation. It's just one that involves partial derivatives. It's one that's partial about the equation. And now, if it's linear, And then, of course, you can add solutions, and so so the most general form then, the most general solution of the homogeneous equation, fh, say, of x will be some sum aj fj of x, where these are all solutions, L on fj is 0. So this will be, let us say, the most general solution of this homogeneous equation. On the other hand, you can consider the same differential operator, but now equal to some source term. So now we have an inhomogeneous linear partial differential equation. But now if, because it's linear, L of F1 minus F2, if we have two solutions of the inhomogeneous equation, then this is LF1 minus LF2, this is S minus S, this is 0. So it's the same as the argument over there, namely that F1 of X minus F2 of X is some sum AJ, FJ of X. My notation now is terrible. I should have stayed with the Y notation for homogeneous, so let me just do that, just to make it a little easier. And then so I'll just use Y for solutions of homogeneous Yj. And okay. Now then, what we would do is we would say that the difference of any two solutions of the inhomogeneous equation is, of course, a solution of the homogeneous equation, and consequently we can write an arbitrary solution of the inhomogeneous equation as any old solution of the inhomogeneous equation plus the complete solution of the homogeneous equation. So for partial as well as ordinary differential equations, linear, the general solution of the inhomogeneous equation is any old solution of the inhomogeneous equation plus the general solution of the homogeneous equation. And what people normally do when they quote this theorem is they say a particular solution of the inhomogeneous equation. Particular is just another way, a shorter way of saying any old solution. Okay, notation for derivatives. I may have, I don't think I did mention this last time. We sometimes say f prime or df dx. Obviously that saves us a lot of writing. And we can say f double prime for d2f dx squared. That's a good notation. For time, we often write f dot for df dt. And f double dot is second derivative. On the other hand, for higher derivatives, it gets a little confusing to write lots of primes and lots of dots, and so one often says this: fk of x, for example, is dk f dx to the k. And if you have a function of two variables, one might say fk comma L of x and y is partial k plus L of f partial xk partial y L. So that's sometimes used. On the other hand, there's another notation that's even more economical and people like to use. F sub x or f comma x is partial f partial x. And one can also use this as a total derivative if you want. It doesn't need to be a partial. It could be just f is just a function of x, in which case it should be an order derivative. and you might even write fx, y, or f comma x, y. And, well, you wouldn't, yeah, right. And this would be d3f partial x partial y squared. So that's another notation. And now, this is fine if we just have x and y, or maybe even x, y, z, but if we're talking about functions of space-time, we typically write if x is a space-time variable, then we write this as x0, x1, x2, x3. This is one conventional way of writing it, particularly if you're doing relativity. And x0 is often written as ct, x1, x2, x3. Now, this is the same as ct, x1, x sub 2, x sub 3. But we normally say this, that x sub 0 is minus x super 0. Then this is a way of building in the minus sign that occurs in special and general relativity, because you have a plus sign for space variables and a minus sign for time variables. Unfortunately, there are two conventions. The other convention is that you have a minus sign when you lower the index on a space variable and not on a time variable. And unfortunately, these conventions are about equally popular. And it's really unfortunate. I think that the better notation is the one where you have 3 plus signs and 1 minus sign, rather than 3 minus signs and 1 plus sign. The other thing, in particle physics, the Rome convention is more popular. Although Weinberg, who's probably the best particle physicist, uses the right convention. Okay, so where was I? Okay, so there are all these different notations, and well, I think I've said that. You can read the rest of it. Okay, so I'm going to skip now to some really important things: gradient, divergence, and curl, and in particular, I want to try to make this as clear as possible. So here we're talking about orthogonal coordinates. And so orthogonal coordinates, of course, are Cartesian coordinates, which are manifestly orthogonal, but there are others that are cylindrical, spherical, and then there are several others that are useful if you have certain kinds of special partial differential equations. It turns out to be best to use some other set of coordinates. Depends on your problem. But for practical purposes, the ones most used are rectangular, cylindrical, and spherical. And so here's the really important thing. The change in a point is some scale factor, h1, a unit vector, e1, a change in coordinates, u1, plus, and I'm doing this all in 3 dimensions. 3 dimensions of space. So I was talking a little bit here about space-time. Okay, thank you, Professor. Forget about space-time. probably the rest of the course. Well, actually, no, I'll pick it up again in about 5 minutes. Okay, so orthogonal coordinates means that we have unit vectors, EI dot EJ equals delta IJ, and we also mean E1 cross E2 equals E3 and so forth, and in fact, EI cross EJ equals epsilon IJK EK with a hat. The hats mean we're talking unit vectors. Epsilon IJK, of course, is epsilon 1, 2, 3 is 1, and this is totally anti-symmetric. Totally anti-symmetric. So in particular, epsilon 1, 1, 3 is 0 because it would have to be anti-symmetric, and yet when you interchange these two ones, obviously nothing happens. So the only thing that's equal to minus itself is 0. And on the other hand, for example, epsilon 2, 1, 3 is minus 1. Okay, so these basically, that's what's meant by orthogonal coordinates. What's meant is that when you change the coordinates, U1, U2, U3, a point, when you change the coordinates by an infinitesimal amount, a point moves in this way. These H things are called, I guess they're called scale factors. And let me just say one thing that's kind of important. The U's are the coordinates that we use, and the coordinates in a fundamental sense, the coordinates are mental quantities, whereas the point is a point somewhere in space, and that has some physical meaning. And in fact, the basic idea of general relativity is that the points and the distances between points are physical, whereas the coordinates are just things we make up. And of course, that's true. All right, so now let's use orthogonal coordinates. Of course, in general relativity, you use arbitrary coordinates. You don't need orthogonal. So that's delta P, and what's the gradient? Well, the gradient is defined such that the change in the function, and the change of the function, of course, is partial f, partial u1, du1, plus partial f, partial u2, du2, plus partial f, partial u3, du3, because f is a function of u, it's defined in terms of coordinates. We say that this is equal to the gradient dotted into dp. And so that means it's gradient f1 dotted, let me maybe rewrite this. So the gradient, I'll rewrite this whole thing really explicitly. So it's gradient f1 e1 hat plus gradient f2 e2 hat plus gradient f3 e3 hat. So that's the gradient, and that's dotted into dp, which is written there, namely h1 e1 hat du1 plus h2 e2 hat du2 plus h3 e3 hat du3. Okay, so this dot product has to be this. And we already know that these unit vectors are orthogonal. And consequently, when you do this dot product, what you get is delta F1 H1 du1 plus delta F2 H2 du2 plus grad F sub 3 H3 du3, and the parentheses go like this. Okay, so then we realize that if this is equal to that, then we have to have grad F sub I times H sub I. The du's are arbitrary, equals partial F partial ui. And so the ith component of the gradient is 1 over hi, the partial of f with respect to ui. So that's the basic rule that defines the gradient. And the derivation I just went through, of course, is very simple, but there are a few moving parts there, and so you should make sure that you understand them clearly. So in particular, for rectangular coordinates, all the h's are 1, and so we just have that grad f is just, in rectangular coordinates, it's just partial x, partial y, partial z of f. So that's completely straightforward. In cylindrical coordinates, we have dp is rho hat d rho plus rho phi hat d phi plus dz. And so the gradient in cylindrical coordinates is rho hat partial f partial rho plus phi hat over rho partial f partial phi plus, of course I left out the z hat. Z hat partial f partial z. In spherical coordinates, so this is cylindrical arc. In spherical coordinates, grad f is r, well, I should have said what df is, if you know what df is, but let me just say it again. dp, I mean, is r hat dr plus r theta hat d theta plus r sine theta phi hat dp. So that's just what you get from drawing your coordinates with polar angle theta, and you bring that down like that, and this angle here is phi. And so when you change theta, you have a moment arm, which is r. That's why there's an r d theta. When you change phi, you don't have the full moment arm, but you have this. I should have drawn it the other way. All right, so this is theta. This, well, I don't know why I drew that. And this is r sine theta, and by that I mean a vector, a length here that's the same as this length down there, and this angle is theta. So that's why this is r sine theta. When you move d phi, you have that's how much the point p moves. And so the gradient in spherical coordinates is r hat partial f partial r plus theta hat over r partial f partial theta plus p hat over r sine theta partial f partial p. Spherical coordinates are a little bit complicated, and if you think that you're going to be asked to do something in spherical coordinates on a final exam, you might get very nervous because of all these funny relations. On the other hand, spherical symmetry is really marvelous, because when you have a problem with spherical symmetry, it's just so much easier than a problem with no symmetry. And the same thing is true with cylindrical symmetry. If you have cylindrical symmetry, it's a lot better than no symmetry, but it's not nearly as good as spherical symmetry. All right. Any questions? I finished. So that's the gradient. Any questions? Yeah.
You mentioned other coordinate systems. What other coordinate systems might be out there?
Oh gosh, I have never seriously, I think a few times I was confronted with a problem that had, say, two particles, and you're thinking of two particles, and you imagine the field that's due to the two particles. Then there's a special set of coordinates that's more appropriate for that. So I used it back then, but I have not used special system of coordinates very often.
Is it like a hyperbolic kind of coordinates between the two of them?
The place to look for this sort of question is, or one place, is Morse and Feshbach. Their two-volume treatise, they mention that, we'll get to a certain differential equation momentarily, and there are 11 different orthogonal coordinate systems in which, say, Helmholtz's equation in 3 dimensions is separable. We'll get back to that in a moment. But I don't know. Keep in mind, though, that from the point of view of general relativity, you use arbitrary coordinates. And the Einstein's insight was, or one of his many insights was that we shouldn't think that any particular set of coordinates is preferred, because nature really doesn't care what coordinates we use. And if nature doesn't care, it must mean that we can use arbitrary coordinates. And that sort of thinking has permeated physics more and more in the last 100 years. All right, how about the divergence? Well, the divergence of a vector, suppose we have a little vector, a point here, and it's inside a cube. So here's our little cube, and we have a point somewhere inside there. Then the divergence of the vector is the integral of v dot, let us say, ds over the surface of the cube divided by the volume of the cube. So you integrate v over the surface, and ds is always the outward normal, like that, and the v is whatever it happens to be on that surface. And so if we imagine computing this surface integral to lowest order, say, the surface integral is, well, first of all, what are these surfaces? These, I mean, what is the surface integral? Well, it's going to be a partial of, let us say, V1 H2 H3 with respect to U1 plus partial of V2 H1 H3 partial U2 plus partial V3 H1 H2 partial U3, and it's that. So the whole surface integral. So maybe I should have written this down. Okay. So why do we do this particular thing? Well, we want to know if we're going in the U direction, in the U1 direction, then I don't know why I drew so cockeyed. Suppose this is DU1. So as you go DU1, the three things can change, where the V1 can change, and the two scale factors, H2 and H3, which determine the area, can change. And so what we do is we multiply by DU1, multiply the partial derivative by DU1, and then we have DU2, DU3, which give us the area. And so when we divide by the volume, the volume is just, it's this times H1, H2, H3. And so dividing by the volume, what we get is that divergence of V is this. And now I can just divide by H1, H2, H3. The DU's all cancel. So that's the divergence, and that's the general formula for the divergence, and so that you can compute each of the divergence. You can compute the divergence in any coordinates. Let me, just to save time, write down what it is in spherical coordinates. We've got well, what is H1, H2, H3? In spherical coordinates, H1 is 1, H2 is R, H3 is R squared, R sine theta. So this is R squared sine theta. That's the product of the three scale factors. And then what we have is partial of V sub R times R squared, partial R plus partial V theta sine theta, partial theta. And let me see, there's an R here, and then we have partial VB, and that would be R sine theta. It's actually partial of R sine theta, partial phi, and no, I'm sorry, it's H1, H2, there's just an R there. Anyway, it's written correctly in the notes and in the book, but, and this one, actually, I've also got this one wrong. This, oh no, this one actually is right. Okay, so when one finishes, oh, there's a sine theta I left out. I should have just written down the answer. 1 over R squared, partial V sub R, R squared, partial r plus 1 over r sine theta partial b theta sine theta partial theta plus 1 over r sine theta partial b phi partial phi. Okay, anyway, this is the rule, and then you just basically fit it in. And this, because we've defined the divergence as the surface integral divided by the volume, one of Stokes' theorems follows immediately, because we can imagine integrating del dot v d volume, so that means we pull the volume over here, and that's equal to the integral of v dot ds over the surface of the, so this is true for the tiny cube, and then if you put together all your tiny cubes, the surface faces that are internal, cancel, and so you get the Stokes' theorem, which is the integral over the volume is equal to the integral over the boundary of the volume. And boundary is often written in partial sign. And the Laplacian now, of course, is the divergence of the gradient. So del squared f, which is often written as just triangle f, is the divergence of the gradient of f. And if you just combine the two rules, you get 1 over h1, h2, h3, sum k equals 1 to 3, partial uk of h1, h2, h3 over hk squared partial f partial uk. So that's the general formula for orthogonal coordinates, and in spherical coordinates it has the form Laplacian f is 1 over r squared partial r squared partial f partial r plus 1 over r squared sine theta partial theta sine theta partial f partial theta. So this is the part of the thing. The complexity here can make you feel that you never want to deal with spherical coordinates, but in fact, you're always better with spherical coordinates. It's always simpler. You have the extra symmetry. Okay, so let me leave that at that point. And now we have the curl, and in the curl, what we've got is we've got two vectors, I say ei hat dui, and then we have another one, hj ej hat duj. And these are two vectors of different lengths, and if we take the cross product, we get the area, we get ek times the area of the rectangle. I said square in the book, but it's really a rectangle. So the rectangle whose sides are these two vectors. And so the curl is defined by saying that the dot product of the curl into the area vector being this thing, is the line integral of the, I guess I'd call it dot dl, around this rectangle. And so if we work that out, say over here, we see that this curl, this thing is going to be just EK, so this is going to be EK at, assuming I've chosen this as 1, 2, 3, so we get a plus sign. It actually, so in general it would be epsilon ijk, and let's say no sum. Then it would be hi, hj, dui, duj. So that's the area vector, and this is just plus or minus 1, and we're not summing. That's the area. And so if we dot that into the curl, what we get then is just curl of v sub k times hi, hj, dui, duj is equal to this line integral, and it's the line integral along the two edges here. One edge is length hi dui, and the other one is hj duj, and we have to allow for the change in these lengths as we go across in these different directions. So we have partial of hj dj, partial ui, minus partial j hi vi, partial uj, and it's all of that dui duj. God, I hear a lot of talking, and I hope nobody's particularly contagious. Everything else said. Okay, so what we have then is, again, with the no sum convention, we have curl of v sub k is 1 over hi hj, partial hj dj, partial ui, minus partial hi vi, partial uj. And so what one often does is writes these in terms of this epsilon ijk, which is named after an Italian physicist named Levi-Civita. In that case, we say curl of v is, so now I am summing over ijk equals 1 to 3 epsilon ijk ek hi hj partial hj vj partial ui. So this is the general form of the curl as an actual vector. And another way of writing it is as a determinant, and then that's 1 over h1, h2, h3, determinant of h1 e1 hat, h2 e2 hat, h3 e3 hat, and then d1, d2, d3. By 1, 2, 3, I mean with respect to u1, u2, u3, and then h1, v1, h2, v2, h3, v3. So it's that determinant. And of course, what I'm using here is the anti-symmetry and the structure of the determinant. I'm not saying that we somehow take this thing which involves vectors and squeeze it down until it becomes a number. This is still a vector. And because of the way this has been defined, that the dot product of the curl with the surface element is the line element of V around the perimeter. If we integrate this curl of V dot ds over a whole surface, an arbitrary surface, what we get is the integral of V dot dl over the perimeter of the surface, because all the interior lines cancel, whereas the surface part, they all add. So that's again one of Stokes' marvelous theorems. Okay, so now there's an important concept which is that some partial differential equations are separable. And when they are separable, okay, why don't we move this a little bit?
Yeah, you can.
Well, it's not that I want to plug it out, but I just want to, if I trip,
No,
it's an apple, so it'll detach without a problem, right?
Yeah, so you can plug it out.
Take it out? Oops. Okay, separable. Partial differential equations. And the idea is that you have some partial differential operator, let's consider just a homogeneous case, then, and this might involve several independent variables, x, y, z, r, theta, phi, whatever. But if this differential operator is such that you can rewrite this as saying that this is equivalent to L1, we can write F as ABC, say, and L1A equals 0, L2B equals 0, L3C equals 0. So this is, then we say the thing is separable. And so let's look at some examples. Minus the divergence of the gradient F equal to K squared F. This is called Helmholtz's equation. And this is separable in fact, I think this is separable in 11 coordinate systems. We're only going to talk about 3 of them. And obviously, well, first I talked in the notes here, I first talked about 2 dimensions, and so we can say f of x and y. Well, what we do is we just write it as x of x and big Y of y. And now if we're in rectangular coordinates, this is minus d2f dx squared minus d2f dy squared equals k squared f. But now if we write f as xy, then this is minus y of y partial to x partial x squared minus x of x partial to y partial y squared is equal to k squared xy. So we just substitute for f xy, and then if we divide by xy, we get the equation minus, let me write it this way, x double prime over x minus y double prime over y is equal to k squared. And now we have something that's surprising and puzzling when you see it for the first time, but since you guys are mostly graduate students, you've seen it several times. And this is just a function of x, this is just a function of y, and this is just a constant. And so that means that this the only way this can be consistent, if this is one constant, that's another constant, and they add up to k squared. And so what we say is that we say minus x double prime over x is a squared, and minus y double prime over y is b squared, and then what we have is a squared plus b squared equals k squared. And notice, because the equation is linear, the differential equation, the partial differential equation is linear, we can add solutions. And so we can say that our general solution f of x and y is in fact some integral dA, integral dB, arbitrary weight function, a for arbitrary, of a and b, the solutions of these equations. And the solutions of those equations are sine or cosine. In fact, there are two solutions of this, two of that. And so the easy way to write this is e to the I ax e to the I dy. And so we've written it as a Fourier transform, effectively. Okay. Well, it's similar things happen, although rectangular coordinates are so much simpler than the other coordinates. But if we go to polar coordinates, then the equation would be, for example, in polar coordinates, we would have, we would set f equal to rho of rho, that's a capital B of rho, phi of phi, and we'd substitute into the equation minus Laplacian f equals k squared f, and then what we would get would be rho double prime phi plus rho prime phi over rho plus rho phi double prime over rho squared. So this is what happens when we put it into the Laplacian and cylindrical coordinates, ignoring the variable z, and we get that is equal to minus k squared rho phi. And now dividing through by rho phi, what we get is rho double prime over rho plus rho prime over rho plus rho squared k squared equals minus phi double prime capital Phi over capital Phi. And that has to be some constant n squared, and in fact what we say is that phi is e to the I n phi, or we could say a linear combination of sine and cosine. But the n, notice, n has to be an integer if the thing is to be single valued, going around the whole circle. And there's a subtlety here. The question is as we take the coordinates phi from 0 to 2 pi, is all of that region physical or not? If all of that region is physical, then we have to have n an integer because the thing has to be single valued as we go around. But on the other hand, not all of that is physical. Well then, we don't need to have n integer. And you might say, well, what is he talking about physical? Well, suppose you were dealing with a problem of cylindrical symmetry. Suppose you had an electrodynamics problem that looked like this. So this is one of the problems that Jackson tortures students with. So you might have, I should have drawn this as actually a circle. So suppose this thing is like that. All right, so this is the center of the circle. That's a little better. Then, and suppose the Jackson problem is, what is the E field here if you have some sort of a charge distribution on this, and let's say this is vacuum. You might have gaps, tiny gaps here. This might be grounded. And this might be, this cone here might be at some potential V, okay? So then if you wanted to solve this, what you would do, you'd say, and you might use cylindrical coordinates, especially if you imagine that that was the Z direction. Then you'd say, well, this is physical, phi going from 0 to whatever this is, maybe 300 degrees. That's all physical, but n doesn't have to be an integer, it can be an arbitrary real number now. So that's the subtlety that shows up in these cases. Anyway, in the cylindrical case, what you do is that's phi, and if you're in the single value, if you're in the case where n is an integer, then this is a Bessel function, and you just say rho, what do I call it? Kn of rho is then Jn of k rho, and this is then a Bessel function. And the Bessel function then has to satisfy the equation x squared Jn double prime. Here I'm letting x equal k rho. Then it's x squared j double prime plus x Jn prime plus x squared Jn equals n squared Jn. So this is Bessel's equation, and so that's basically how that works. So I guess we're basically out of time. Is there any questions? I thought we'd get much further. I guess not.
Is there any rule for choosing the separation constants?
I'm sorry, say it
Any
again?
rule for choosing the separation constants?
Yeah, these things I think are called separation constants.
I mean, you can get different functions depending on how many signs you choose.
What?
You can get different functions.
So A and B are just numbers.
Well, if you're in 3 dimensions.
No matter how many dimensions we are, A and B are just numbers. I mean, in other words, when we have something like this has to be a number, that's a number, that's a number. That's in 2 dimensions. Or in 3, once we separate things, they all have to be numbers, because it's a function of x, it's a function of y. And this is not a function of anything, it's a constant. So the only way this can be consistent is if this is one number, this is some other number, and that's a third number, and then they add up in this way. It's very surprising. But all our calculations, all physically fall apart if we didn't have this simplification. Why don't you ask me after class if you're still confused? I think we're done, right? You can turn it off. But